Hello everyone. Our group decided to make an essay on making use of big data. My name is Gustavo Fonseca and my colleagues are Pedro Cotovio and João Monteiro. In this presentation, we'll do a brief introduction. We'll talk about big data and deep learning. Then we're going to go through the three papers that we chose. The first one does a comparison of Apache Spark and Apache Flink, two frameworks that are used to handle big data. Then we have the next two papers focusing on deep learning. The first is a review paper going around the applications and challenges, and the second one goes on uh, a way to check on the performance implications of big data when we're scaling on deep learning. And then we finish off with a conclusion. So on introduction, big data, when we talk about big data, as we talked in class, there's the three V's that we should take in mind. One is variety, another one is in the name, it's the volume of the data, and the other one is in velocity. And this is just all of these are continuing to increase. We have a velocity now increasing with 5G, which is going to become accessible to everyone quite soon enough. Volume, it's proven by the zettabytes of data that we currently have, and it's just going to continuously exponentially increase. So what happened when we do it with this essay, we wanted to discover then these frameworks and some of the algorithms that we should use in these cases to handle all this big data.
On the first paper, a comparison on scalability for batch big data processing on Apache Spark and Apache Flink. The goal was to assess which framework performs better when the amount of data increases over time. This goes in agreement with the necessity for high-performance big data analytics tools in today's world. In the past, there wasn't many data lying around, but nowadays and in the future, the huge amounts of data produced every day, structured and unstructured, need for real-time analytics performance tools. Long after the introduction of the MapReduce technique in 2003, the data processing world is still evolving. Apache Hadoop came along with an implementation of MapReduce, but this tool presented many limitations that no longer hold in today's standards. In more recent years, Apache Spark was introduced to the market with improved technology to tackle the limitations of MapReduce. It allowed for the loading of data into memory and querying it repeatedly. It also works on top of resilient distributed datasets, making it fault-tolerant by nature. Apache Spark also manages to process real-time data using a micro-batch technique. Apache Flink is more recent and was developed to natively work with very large amounts of data on low latency, and be naturally able to process data streams in real time. With this, the authors managed to evaluate the performance of these frameworks by comparing the runtime of three different machine learning algorithms: support vector machines, linear regression, and a custom implementation of distributed information theoretical feature selection. Worth noting that Spark has two machine learning libraries, MELlib on top of resilient distributed datasets and MEL on top of data frames. The post-processed dataset had 65 million instances and was progressively randomly sampled from 10 to 100% of the total dataset. From the table, we can see that MELlib performance is much better than the other two. We can conclude that Spark performs much better than Flink. This can be due to the fact that Flink is a more recent framework and Spark is old and already refined.
On the second paper, we're talking about deep learning applications and challenges in big data analytics. This is a review paper. To start, deep learning is taking a huge amount of unsupervised data and it's turning all that into a complex representation of it. Now, this complex representation will include the global relationships and patterns in that complex representation. And this is perfect for feature engineering, since instead of recurring to experts to understand the main representations that are in the data, we can just make sure that the data itself contains all those relationships. And one example of it is for example, for indexing. Instead of tagging books with, okay, this is horror, this is terror, this is romance, we can just give word vectors of books, and this is another paper by Internetal, and they give on the lower layer of an algorithm, they would get the deep learning algorithm, they would give word vectors, and the higher layer would give out 128-bit vectors representing. So this is the complex representation of each book. And one way to query these bits of code to understand which ones were closer related to others would be by using by recurring to a Hamming distance. So the more similar these 128-bit vectors were to each other, the closer these books were in terms of topics. And so what can we do with these outcomes? So this, as I said, there could be used for indexing purposes and keep data closer together with the ones that are more similar. Another way is to we could use it to discriminate data and tagging, and this is different because we use the abstract representations as features, which can then be used to perform to a discriminative task of data tagging, and then used for indexing. And this is then be able to apply other machine learning algorithms on top of these new complex data to form new predictions. And apart from all these applications, there's also the challenges, and they have a lot to do with characteristics of big data. One of them is how fast it is, and because it is so fast, and it can come with a lot of noise and stuff and problems in the data, which need to be filtered or corrected. And a lot of this can also be handled with autoencoders. The high dimensionality of the data with handling photos, videos, and a lot of other stuff. So there's a lot of things that are a lot of features that we're being given by each of the data. So we need to be able to work with all of this, and this is very demanding and requires a faster algorithms. And then we have the scalability of data, so the volume keeps on increasing as well, the amount of data that we're receiving. And there's some examples already, as in not so practical ones, as in having to use tens of thousands of clusters to train billions and billions of parameters. But there are others that have managed to make use of just 16 machines to train 11 billion parameters. So yeah, this is some of the challenges, and the authors also give out some things to focus on. One of them is the data sampling. So we're collecting this data, the domain adaptation. So we're given data from one domain, and how are we adapting that to the domain that we're going to apply that data, that information to. Now we also need to define the criteria for doing these complex representations, because there's an infinite kind of way that we can represent data, but so we should be able to narrow down exactly the representation that we want the deep learning algorithm to give us. And then how are we making use of all of this? So with a semi-supervised learning that allow us to define criteria for good data representation learning, and we could also make use of active learning. So by crowdsourcing or human experts to help us label this data and make more use out of it.
So now I'll discuss a bit of our final paper. This paper tries to analyze the performance issues that deep learning frameworks normally have when using big data. Um, Pretty simply from a IO point of view, so the data use, how the data is used, how it's stored, and the networking that it's needed, and try to evaluate the performance issues, or what is causing more performance issues, and compare this with the normal analysis, which is um, more compute power analysis, more normally related to deep learning algorithms. So normally this mixed solutions of deep learning and big data are not very well understood by their users and by the designers of the structures and the framework. So normally we end up having kind of a brute force experience when we have normally a lot of computing power, but not actually structured in a way that it accomplishes something useful. So this author tries to explore the I/O point of view, as I said. Well, by exploring this point of view, we can learn to structure our framework in a way that the computing power works with the data flow, and we get a more efficient framework for normally less money, because most of the times these frameworks are very expensive, and there are a combination of both high-end computational clusters and high-end networks and high-end data storages, but they don't actually work together very well, so they don't accomplish their objective. So we probably will need some expensive tools to do this, but probably we can do this in a more cost-efficient way. So first of all, I like to say that in this paper we didn't explore very much of the actual results, because this is a performance paper. There were made many experiments by the author before he reached any conclusions, and but in this, as we have a short time, we actually didn't get to enter this. But in our previous essay, we got a little bit into what was actually happening in terms of performance, and if other students or the professor has any interest, they can refer to the paper, which is very interesting, and for sure we can have a better understanding of why this is happening. But I'll try to explain it in a short way. So we'll not discuss the results, but we'll discuss the conclusions that the author arrived to. So one of the very interesting conclusions, very obvious conclusion also, but very interesting, is that performance is largely determined by storage and network bandwidth, where typical approaches tend to focus on computing power. Yeah, but computing power needs to be complemented by network bandwidth, because we can have clusters with computing very big computing power, but if they don't actually have the data there at a certain rate, they cannot train anything. So it's essential when I have big data, and especially in streaming data, that we have a very strong bandwidth and a very strong storage system, so we can connect our data very very fast to the actual nodes that we are using. One of the things that we most see in the related work is that many papers explore the way that you should store the data in, for example, if you should store the data in individual files, or if you should store the data in for example, a key value database. But what the author actually can prove with his experiments is that the storage solution does not influence very much performance. It can influence, but it's nothing compared with bandwidth. If we can have the clusters and the nodes in the clusters have the data there at the rate that the computing elements actually need them, so at the rate that the algorithm is actually able to process information, if we can get that at that rate, we don't have any latency related to I/O. So the storage solution, it ends up not mattering in this. So, or at least not as much as the bandwidth. So the bandwidth is the most key in big data, because, as I said before, uh, the first thing that we need to establish is a pipeline to make sure that our data gets to the clusters at the rate that they need them. If we cannot assure this, we don't need that much computing power, because it will not be used, because we are not able to get data there. So we need to make sure that we can get data at a certain rate, and then we can set up the computing power for that specific rate. I think the biggest and conclusion, and the most interesting conclusion, is this last one, which is caching in memory or local disks can increase performance. This is also a seems very obvious solution, but it's not. It's almost never used, and at least when this paper was released in 2018. But it's quite obvious, and it can prove very useful, because when training deep learning algorithms, and in machine learning in general, but especially in deep learning and neural networks, training reuses data a lot. So we will be ending up using the same data a lot of times, and if we need to fetch the data from a database that it's not located on the node, every time that we need, we will have an extra I/O time related to that. So we can just avoid this by having data there. If we cache everything in memory, it will be very fast. If we cache everything in a local disk, it will be much faster than fetching the data from a database. Obviously, many times when we are talking about databases with millions of images or other types of data, millions of records, obviously we normally cannot cache this in memory, because it's very expensive to do so, or it's simply not possible in some cases. But at least we can cache it in the local disk, which will avoid sending another fetch request to the database or the data storage that will save us some time. So this is an obvious solution and a very helpful one. So with this conclusions, the author creates a set of rules that can really help to build a better deep learning framework using big data. In a very concise way, the rules are: size of bandwidth should be according to the size of the cluster. So they have a linear relationship, as I explained. We need to make sure we have a certain rate of bandwidth, and then accumulate a certain computing power, a certain cluster type, or a certain number of nodes, that we have for sure the rate needed of bandwidth to get the data at the data flow at a certain rate to those nodes. So that's a very important step, to be cost efficient. It will not affect the performance directly, but it will affect the cost that we are having, that it's not being used. So we can have more computing power, and that will simply not influence the performance. So we'll want to have the least computing power possible while having the best performance. So if we can have a better bandwidth, then we'll invest on that. And then if we can, we invest on computing power to linear relationship. So normally the networking side or the bandwidth side is overlooked, and there's more investment on the computing power, but as we've seen, this does not make sense. Another thing is to equip nodes with as much memory as possible, and this goes back to what I already talked to, but and it reaches to the third rule, which is cache training data in memory or in disk when possible. So we want to invest in memory, because if we can avoid having to make networking fetches of memory. Obviously, in streaming, this is not possible in streaming data, but in data sets that are already set up, we can just cache everything normally on disk, and we have some I/O latency, but not as much as we would have if we had to fetch the database. So I'm already over time, so I'll end up here. But I would like to say that if you have interest, you should go see the paper because it's very interesting. And if you intend to build this type of infrastructure in the future, it will be a useful tool for sure. So I'll now refer back to my colleague.
In conclusion, we can say that Apache Spark presents better performance and Apache Flink still needs to be developed. Big data will continue to get bigger and computing power will increase. We can also continuously develop better frameworks and algorithms to accompany this increase.